We now consider the following example. If we go from 15 meters per second to 35 meters per second, between clock times t equals 8 seconds and t equals 12 seconds, what can we determine from that? Well, if we think we go from 15 to 35 meters per second, if our acceleration is uniform, then our average velocity is going to be 25 meters per second, halfway between 15 and 35. We add the 15 and the 35, and we get 50 divided by 2, we get 25. That's halfway between 15 and 35 meters per second. We can also determine that the change in velocity is 20 meters per second, and that takes place over a 4-second time interval. A 20 meter per second change in 4 seconds is an average rate of change of 5 meters per second per second. The situation we have can be symbolized. We are given the values of 3 variables, delta t, v naught, and vf. We're asked what we can determine from these 3 variables. You might want to pause and ask yourself, what can you determine if you have v naught and vf and delta t, and how would you go about determining it? Okay, whether you've paused or not, we're going to go on. You see that what we did in the example was we averaged the initial and final velocity and then multiplied that by the delta t in order to get the displacement, and we subtracted the initial from the final and divided by delta t to get the average acceleration. And of course, if the acceleration is constant, average acceleration is the acceleration. Now we diagram this process as follows, or as you see here. I'm going to call this a flow diagram. It's the flow of our solution sequence. From v naught and vf, from the 15 and 35 meters per second, we determine our delta v, our change in velocity. It turns out that's vf minus v naught. Okay, we subtract v naught from vf, and we make a note of that when we write this down. So we have our delta v from v naught and vf. And then once we know delta v, we put that together with delta t to get our acceleration, which is just delta v over delta t. Of course, since delta v is v naught minus vf, we go ahead and write that as vf minus, it's vf minus v naught. I said that backwards. But we write vf minus v naught over delta t, and our acceleration is equal to this expression. Often, we will solve this for vf. Multiplying by delta t, we get a delta t. Adding v naught, we get this expression. vf equals v naught plus a delta t. That is one of our fundamental laws of uniformly accelerated motion, one of the fundamental equations. And the other equation, the other of the most fundamental equations, comes from averaging vf and v naught to get v bar equals vf plus v naught over 2, and putting that average together with our delta t to get delta s equals v bar delta t. Since our average velocity is what we get when we add the velocities and divide by 2, we substitute that and we get this expression and this equation. Delta s is vf plus v naught over 2 average velocity multiplied by the time interval. And this is our second of the two most fundamental equations, both of which come out of considering the situation where we know v naught, vf, and delta t.